Hello, I am Kevin. I am one of the instructors at the Sacramento City College Aircraft Maintenance Technician program, and today we are going to take a very in-depth look at the Marvel Schebler MA-3A carburetor. Now, this little carburetor is used on small aircraft, say about a Cessna 150 at about 100 horsepower or so type of engine. This particular carburetor does not have the accelerator pump system on it. So if you're looking for a carburetor with the accelerator pump system, that is going to be in a different video. But the great thing about this one is it has some options that the accelerator pump system does not. So stay tuned for that. All right, let's jump into this carburetor. Like any aircraft carburetor, I like to divide this up into two basic systems. You have your idle circuit and your off idle circuit. So idle circuit's going to be your when your engine's idling, anything up to about 1,000 RPM. Anything over 1,000 RPM, we're pretty much looking at an off idle system. So off idle system is what we're going to look at first. But to get acquainted with this carburetor, let's take a look at a couple of items on here. So number one, over here we have the throttle shaft, the butterfly valve or the throttle plate, and we have the manual mixture control over here. And we'll talk more about this stuff in the setup towards the end of the video, and also a couple of things about airworthiness directives too. All right, so let's take this off right here and take a look at what is going on and how this carburetor operates. There we go. So on the inside, you can see we have the float bowl over here. We have the floats over here, and we'll talk about each one of these things as we go. All right, so let's turn the page here and take a look at this drawing here. Now, I know this does say model MA-4 SPA, but this is the drawing that is provided by Marvel Schebler to cover both the MA-4 SPA and the little MA-3 carburetors as well. So there's some differences, but for the most part, this is going to walk us right through it without any problem whatsoever. Although I will admit I had to make a few corrections to the drawings. All right, so to start with, how does the carburetor work? Well, let's talk about we're a drop of fuel, and let's take a look at the passageways and the path that fuel is going to take. All right, so to start with, fuel is going to enter here. And there is a screen in here. So that screen should be checked every, say, 100 hours or annual. I would say no more than that. I like to check them every time I do at least an annual 100-hour inspection. We don't want any debris clogging the fuel path. That would be a problem. All right, so fuel goes through this into this chamber right here where it enters the needle and seat area. So now this, of course, is upside down to the way it sits on the aircraft. Normally it is sitting this way. I'll move it just to the side so we can see. So when there is no fuel in the float bowl, the floats are going to drop down. And as fuel enters the float bowl, the floats will then float up until it blocks off fuel coming in the needle and seat area. So let's open that up, take a look at the needle and seat area and see what is happening there and how that works. So we'll pull that pin out. By the way, that pin is supposed to be cotter pin. There's a lot of things I've already, screws and such that I've taken out already for ease of doing the video. But here we have our needle right here, and this is the seat right there. So as the floats raise up, that needle right there sits in the seat and blocks off the fuel. When the needle is off the seat here, fuel comes in and out of this hole right here into the float chamber. So it comes out of here, fills up the float chamber until the fuel level gets to a specific height, pushing the needle up into the seat, blocking off the passage of fuel. Now, the level that these floats are at, it's different than some carburetors. We don't actually measure the float level per se, but rather when you get into the instructions, you actually measure this distance right here with a drill bit or calibrated rod, and that's the float level is measured right there, rather than what is the actual fuel level, like a Stromberg, where you'd actually measure the float level in there. So, all right, taking this back off, we'll take these and we'll set them out of the way. We'll pull off our gasket and set that out of the way. All right, so we're talking about fuel came in through here, filled up the fuel bowl, and we are talking about the main discharge system right now, the off idle system. So looking over at our drawing, we can kind of follow along here too. So here's the screen I talked about. So fuel is going to enter right here. It is going to go through the needle and seat and fall down into the float chamber where the fuel will fill up the bowl until it gets to this fuel level right there. There's my desired fuel level. When it gets to that point, the floats will have raised up, blocking the fuel from coming through the needle and seat, stopping the fuel and stopping the level right there. And that's where it will sit until we start the engine. And once we start the engine and the engine is running, then fuel will be used. And as fuel is used, the level will drop down a little bit. And as it drops down a little bit, so will the floats, which will allow more fuel to come in, which will raise the level up and keep the level roughly at that point right there. So, okay, so we have fuel in the fuel bowl, and now we have to get the fuel out into the engine. Well, let's talk just briefly about what is causing the fuel to come out in the first place. So this is an updraft carburetor, meaning that the air is going to come from the atmosphere up the carburetor, through the venturis, out and into the engine. And what is causing the air to move through the carburetor is we have 4 syringes, we'll call them pistons. The pistons are moving back and forth and sucking air just like a big syringe, 4 of them to be exact on most of these little engines. And that is drawing in a rather large quantity of air coming up across 2 venturis in this particular carburetor right here. So we have a primary and a secondary venturi. It's going to pull the air across there. Well, here's our venturis over here, and you can see them. And so the way a venturi works is by Bernoulli's principle, which basically says that as air is drawn across a venturi, the air is going to accelerate. And whenever air accelerates, it is going to have a drop in pressure. So that air moving through these venturis is going to cause a drop in pressure, otherwise known as a vacuum. That vacuum, low pressure, will want to draw fuel out of the carburetor up and into the engine. And the amount of fuel that is drawn out of the discharge nozzle right here will be dependent upon how much air is flowing through the venturi. That would be creating the vacuum versus the air pressure inside of the float chamber. So again, the amount of fuel that is going to come out is going to be dependent on the difference in air pressure between the venturi and the float chamber. And that difference of air pressure is known as fuel metering force, the difference, which is a little strange that we're talking about fuel metering force, which is air pressure, but you heard me right. The difference in air pressure between these two things is called fuel metering force. Now, we could also say that the air pressure or lack of pressure, the vacuum created by the venturi, is known as the air metering force. And we could also say that really the brains of the carburetor is in fact the venturi, because the venturi is what is measuring the amount of air going into the engine and proportionally putting the correct amount of fuel into that air to operate the engine correctly. So that is what is happening right there. Now let's take a look at our carburetor down here. And so we have the fuel, as we talked about in the drawing, is in the float bowl, and it's going to go down through this hole right here. This is the metering sleeve. So we're going to go through the mixture metering sleeve up into this passageway that's drilled right in like this. And we'll take a look. We'll pull out the discharge nozzle. And we're going to look at this passage right here. And you can see right down in there, the fuel comes through that mixture sleeve right there, through a drilled passageway into this chamber in there, where it is going to meet our discharge nozzle. So this is the discharge nozzle right here. This right here on this particular carburetor is called the power jet. So the power jet is the metering device. On other carburetors, we would call it the main metering jet. That's the word I wanted. Main metering jet On this particular carburetor, it's called a power jet. Same thing. So this orifice right here is what determines the maximum amount of fuel that is allowed to go from the fuel bowl into the discharge nozzle assembly. So from the discharge nozzle assembly, the power jet up through here, and then out these holes right here along the side here and right here out into the low pressure area of the venturi. So that's all there is to the fuel, actually, the main system as far as fuel goes, right? Just through the screen, through the needle and seat, into the bowl, from the bowl, past the mixture metering sleeve, power jet, discharge, engine. Very simple. But now we have to make it complicated. You can see that there are a series of holes around here. There are some holes between these threads, which for right now we're going to ignore, and we're going to talk about those later. But these holes right here is one here, one there, and a series of 3 right here. These holes here allow air to enter into the fuel stream to emulsify the fuel. Now we want to add air to emulsify the fuel for a couple of reasons. One, it breaks up that fuel and creates smaller droplets that are more easily evaporated and will allow the engine to run much smoother and cleaner because we can, like I said, evaporate the fuel into the smaller droplets rather than large globules that have less surface area than a bunch of small drops, and so that's better. Number 2, these holes actually help draw the fuel up through the discharge nozzle and out into the engine because of the venturi suction. So we have air right here. Now we got to figure out how that air gets in there. And to do that, we are going to look at some passageways here. Probably the most difficult of figuring this carburetor out is the air passage, to be honest with you, but they're really not that difficult. So we're going to start at the beginning. So this is the inlet to the carburetor as far as air goes. Air went through the air filter on the aircraft engine. On the aircraft, I should say, through the intake system, and then entered into here. So the air going this way is going to go up across the venturi and off into the engine. So any air going in right here is going into the engine. However, this hole right here is where air is going to enter for our air system that we're going to be looking at internally. So we're going to get some air is going to go into this right here, and that is just drilled and comes out right there. So air enters here, comes out of right there, and corresponds to this hole right there. So we have this hole. So air is now going to enter this way. And if we look at it over here, we can see there's a hole here and right there. That is a drilled passageway that drilled right through there. So it tees off, if you will. So this is connected to this, which is connected to this. And at the same time, this passageway right here is drilled down pretty far. We're going to talk about that in a little bit later, but it's drilled down far enough that it hits this T right here. So all 4 of these holes are interconnected. Not that one yet. So we're talking about the air here, here, here. They're all interconnected. So again, air was coming into this one. It's allowed to come out of these 2 into the float chamber. So it's venting our float chamber. And at the same time, it went to this spot right here. This corresponds to this hole right here, which is drilled in a couple ways. One, it's drilled backwards. So right through here into this one. We'll talk about that later. And this is drilled straight down into this chamber right here. So maybe you can see right in that. It's very difficult to see. There's a hole right there. So you have to trust me if you couldn't see it. So, okay, so now we have air coming down this way out of here. So real quick, air up through here, up through here, down this way, into the T, turns the corner, comes out of here, goes down in there, and down into there. And once it gets into this chamber right there, it is allowed to go through these little holes right here, where it mixes with the fuel and discharges out. And that is really pretty much it for the main system right there. We've covered both the fuel and the air a couple of times. Let's take a look at our drawing and just go over it one more time. Fuel came in through the screen, past the needle and seat where it entered the fuel bowl. From the fuel bowl, it goes down through the mixture metering sleeve, through the power jet, which is the limiting device for how much fuel we can get. from the power jet, it enters into the nozzle, if you will. And right in this area right here, it is emulsified with some air. Now, where did this air come from? Well, this drawing is just a slightly bit different than what we have, but the principle still applies. We have ambient air comes down into a teed section that is drilled off into the chamber where the nozzle goes, where it enters with the air. Air and fuel now discharge out of the nozzle due to the venturi and the difference between the air pressure and the venturi and the air pressure on top of the float bowl, which is referred to as our fuel metering force. All right, so there we go. We have covered the main system. Now let's move off to the idle system. Well, thankfully for us, much of the idle system piggybacks on what we've already talked about. But let's talk about, why do we need an idle system to begin with? Why won't the carburetor just run with the system we talked about? Well, the problem we have is that the air coming through the carburetor at idle is significantly less than the air that is coming through the carburetor when it is off idle. So if we take a look at the throttle valve right here and we realize that is wide open throttle, and this is idle, you can see we have very little gap between this plate and what's around it. So right around here is where we're getting air, and there's very, very little coming out there, as opposed to, that's a lot of air. So because we have such a small amount of air coming through right here, that in turn means that we have very little air going across the venturi. And because we have so little air going across the venturi, that means there's really not much suction at all, not enough suction to draw fuel out of the main discharge nozzle. So the main discharge nozzle is completely useless to us because the venturi at this point is useless to us. So we have to have another way of discharging fuel, and that is the idle system. So again, the path is nearly the same for quite some time. It comes through the inlet, across the screen, out the needle and seat, into the float bowl. From the float bowl, it's going to go once again through the mixture metering sleeve and up through this channel, which it did before, into the power jet, which it did before. But instead of moving on into this part of the nozzle, fuel will simply fill up the nozzle. And we're now going to look at these holes. So before I said, oh, we have these holes right here, but we're going to ignore them when we looked at the main system, but now we're not going to ignore them. These are a vital part of our idle system. So these holes are drilled in between two threads, which pretty much isolate them and create their own little passage. And what that does, fuel comes up that power jet and out of these holes and off into the idle system. So if we take a look at our drawing over here, we will see this is right where we were. We had fuel in the bowl. It came down through the mixture metering sleeve, up the power jet into this area. Here's where the top threads are. Here's where the bottom threads are. And these are the holes drilled in between those two threads. It is going to go up into our idle tube. So let's take a look at our idle tube. The idle tube is this passageway right there, and I've already loosened it up so I can pull it out quickly. There we go. Here's our idle tube. Looking at our idle tube, it has a very tiny little hole right there, which is going to be our idle jet, if you will. Just like we had a power jet, here we have the same thing right here. We have the idle jet. So that is the restriction for the maximum amount of fuel that can get up through the idle tube. So the idle tube then, we're going to notice has a little hole right there. And you can already guess what that's for, I hope. And that is going to be for air. But we'll get to the air in just a little bit. Fuel comes up through this tube, out of this hole right there, because that's sitting right there, into this hole right here, and then up. I know it's down this way, but in the carburetor, it would be up. And those holes right there are going to go up into the throttle body area. So let's look at the drawing and we can take a look at how that's working. So we had the fuel going up through this idle tube, carburetor split, and then we have that hole and it went up. So once it goes up into here, we have several passageways. and depending on the carburetor, it may have 2 or 3 or more passageways. So right here, it should have been colored green. I have another one here, green, and another one right here. 1, 2, 3 passageways. Now let's take a look at our carburetor and see if that corresponds to our drawing. So I'm going to close this. It is spring-loaded to open. And thankfully, the fuel has actually made a clean spot. So I can see 1, 2, and 3 right there. Probably can't pick it up on the camera, but 1, 2, 3 holes, just like our drawing over there. These holes are the discharge holes for the idle fuel. And what is causing those holes to act as the discharge nozzle is that when this plate is closed, the area above it is subjected to a significant vacuum. Remember, we have 4 cylinders. Even in a Continental O200, that's 200 cubic inches of air it's trying to draw through with each 2 revolutions of the propeller. And that is causing a big suction right here. Air is not getting through this throttle plate very well, so it is going to want to draw whatever it can from wherever it can. And it just so happens that these holes are exposed to that vacuum, and it will draw out fuel from these 2 holes off into the engine. Now there's a 3rd hole down there, and that 3rd hole cannot be seen right now. So what's happening with that 3rd hole below the throttle plate is that air is actually entering that hole and going up into the tube. So if we look at the drawing, it doesn't depict that. It has all the holes above the throttle plate's open, but when the throttle is closed, we're going to put the throttle right about there, which means that this hole is below that, which means that air is coming up this way and hitting the throttle plate, and this is higher pressure. So air is going to go this way and up, adding an air bleed to the system. So believe it or not, we have 2 discharge nozzles and an air bleed at this particular point. But as we open the throttle up and that hole down there gets exposed, now it's exposed to the suction of the engine. And by the way, the throttle plate opened up more, some more air is getting through, some more fuel is needed. That creates a 3rd jet where fuel can come out because we have more air, we need more fuel. That's how we got it. So added more fuel right there, and that's going to, all 3 of those will discharge until the throttle plate gets to a point where enough air goes across the venturi to start allowing the venturi to create suction to draw fuel out of the main system. So there's a period of transition where we may get fuel out of all 3 of these and a little bit out of here, but eventually as we go up towards cruise power, it's only going to be coming out of the discharge nozzle, no longer out of the discharge nozzles for the idle system. They will just no longer be in effect. All right, so let's go back. Now we did mostly fuel on this. We did add a little bit of an air bleed out of that 3rd nozzle there. So again, that third hole sometimes acts as a discharge nozzle, sometimes acts as an air bleed. But let's find out, where do we get air into our idle tube, into that hole right there? Well, if you remember, a little bit ago, we talked about air coming up through here, coming out of here, entering into here where it's teed off. And this is part of that teed system. So air then goes in this way, fills up the float chamber, and then it comes out of here into this right here that's drilled straight down, which will allow us to get some air into this, but it's also drilled backwards. So if we looked at it, I don't know if we can pick it up on the camera maybe, but it's right there. It's drilled backwards into that chamber right there. So that is where we get our air right there. So it's right before it enters into this chamber, it breaks off and goes that way. We get air into there, emulsifies, comes up through here. Now we have air and fuel coming out of this, air and fuel going into this hole. Passageway is drilled all the way up into here where we have the 3 holes. When the throttle plate is closed, we have 2 discharge nozzles. And when the throttle plate opens a little bit, we have 3 discharge nozzles, and that is the idle system. Now, we will talk about the idle mixture adjustment here in a little bit when we talk about setting up the carburetor. So that is really, in effect, the 2 main systems of this carburetor. So next, we need to talk about something that is a little bit more unique to this particular carburetor, and that is the back suction. Well, more appropriately, it'd be the back suction economizer. So before I can talk about that, let's talk a little bit about economizer and power enrichments. So I'm going to change to this slide right here, and we're going to talk about this. So carburetors are designed so that they are rich on two ends of the spectrum and not rich in the middle. So what I'm talking about is when we talk about rich and lean, we have carburetors are very rich at idle. In other words, they have an excessive amount of fuel per air. It is not what you would call an ideal situation. In fact, it is so rich that the engine doesn't even run at its best power. So again, if we look at fuel systems, we have this term called stoichiometric, which is about 15:1. And at 15:1, it is a chemically pure, perfect mixture where all of the fuel is burned in a cylinder and it gives us the maximum power. And this is theoretical there. It could be different than 15:1, usually is, but we'll go with the theoretical numbers. And then when we get on one side of the rich spectrum, then that would be like 8:1, which is 8 parts air to 1 part fuel. And that is very rich, and we start losing power. Or we can go all the way to the other end of the spectrum, which is 18:1. So we have 18 parts air to 1 part fuel. And that is also not providing the best power because we don't have enough fuel for all of the air we have. All right. So there's the two ends of the spectrum. And then right in the middle, we have the perfect blend, which gives us the most power. All right. So keep that in mind, because we're going to use that a little bit later too. But carburetors are designed to run very rich at idle and also rich at takeoff. And why is that? Well, it is designed to be rich at idle. And I know the FAA books and the FAA test questions all say because there's not enough cooling happening at idle, therefore we need to add extra fuel. That is not true. And I will tell you why in a second. So it is not true. The real reason why our carburetors run very rich at idle is to get them started. We do not have a choke. A choke is simply something that chokes off the air and allows the carburetor to become excessively rich so that it starts easier. Rotax uses something like that. Some planes that use Rotax engines actually have a manual choke. All right. And lawnmower engines and other types of engines, older cars used to use chokes. We don't have a choke, so we run an excessively rich mixture. All right, so how do I know that that's why that is and the extra fuel is not for cooling? Well, because most pilots who own their own engines and care for their engines, as soon as we start our engine, we are going to reach over and we're going to lean out the engine, we'll talk about that in a minute, excessively, to the point where the engine gets just enough fuel to run because we're trying to minimize the lead contamination of the engine, topic for another video. But I can assure you that my engine does not overheat at idle, and I run it as lean as it will possibly run. So lean that if I add any throttle, the engine will die. So my engine does not overheat, therefore I know that to be true. Now on the other end of the spectrum, we want a very rich mixture at high power settings. And the reason why is for cooling and detonation protection. So extra fuel will equal extra cooling for an engine that is working hard and provide a measure of protection against detonation, also called pinging, but we call it detonation in aircraft. Now, we have rich at one end, rich in the middle, but we don't want it rich through the middle here. I think I said in the middle. So we have rich over here at one end, rich on the other end. In the middle, we want it to not be rich. And why is that? Well, because if the only purpose for having a lot of fuel, a rich mixture at idle is to get it started, we're started, so we don't need it there. And we're not at high power settings, so we don't need the extra fuel for cooling. So we want it to have less fuel. Now, it would be possible for the carburetor manufacturers just to make it so the line just kind of went across like this and just got more at idle. And that would be fine. We could deal with that. But in this particular carburetor, they were very nice to us and created what is called an economizer. And an economizer actually uses a function of the carburetor to automatically lean out the carburetor at cruise settings where it's not working hard and we don't need the extra fuel for cooling or detonation protection. So we're using a little bit less fuel. And that is a good thing. Now, a lot of people think that, wow, I mean, are pilots really that cheap where they're so worried about fuel? Well, yes, we are. But more importantly, our fuel contains a massive amount of lead, and this lead is a bad thing from one end to the other. It creates lead deposits, it contaminates the oil, it can cause problems with the valves operating. So lead is not a good thing. If we can lean out our mixture and get more power and less lead effects, that's a good thing. So this carburetor is designed to automatically do that. Now, in this particular carburetor, it is called an economizer. Some carburetors will call it power enrichment. It may do the exact same thing in the exact same way, but they'll refer to it as power enrichment. Some call it economizer. So I don't want to get too hung up on those two terms, but understand that both those terms can mean the exact same thing. If I were elected king for a day, I would call any system that makes the line in the middle go down an economizer, and any system that allowed the line to go up at takeoff a power enrichment. That would make things a lot easier, because then we could talk about carburetors that automatically just add more fuel at high power settings versus carburetors that drop the fuel in the middle. This particular system we're going to look at pulls the fuel down in the middle. It is called an economizer system. So, all right, so let's take a look at our economizer system on this particular carburetor. And the way it works, we're going to use air pressure, and we're going to go back and think about our air pressures in the float bowl versus air pressures in the Venturi, which was called the fuel metering force. So the economizer is going to change the fuel metering force. And the way it does that is through air pressure. Now, what you couldn't see before, and maybe will not be able to see in this particular carburetor, is we talked about these three holes, 1, 2, 3. And hopefully you remember those are discharge nozzles for the idle circuit. Well, what is a little difficult to see is off to the side, right there is another hole that is drilled into this throttle body area. That is the economizer hole. We can see up at our chart right here, the economizer hole right there. And that hole is drilled into a passage into this one. Remember, the air originally came through here, up through here, into here, and then teed off. Well, if we go straight down and keep going, there's a little jet down there that is actually attached to that hole right here. So the way this works is when we are at idle, that hole is covered up and is down in the higher pressure area, because right here is where all the suction is happening. This down here is no longer has a lot of suction whatsoever. It's pretty much ambient air. And so that has no effect whatsoever. It's practically assisting this hole right here. But when we start to open the throttle and we uncover that hole right there, now it is subjected to the low pressure area the pistons are pulling. And when we get a little low pressure suction on that, we're going to get suction here, which is now going to take some of the air that was designed to vent the float bowl and take it away. So it is going to create a lower pressure in this area. Well, if we lower the pressure in the float bowl, if we lower this pressure, then the pressure difference between what is here and what is here at the Venturi is less. So we have effectively lowered the fuel metering force, which means there is less suction on the discharge nozzle, even though there's the same amount of air going through here, and we still have the same amount of suction created by the Venturi. It's just that this is no longer high pressure in the float bowl. It's also getting a little suction to it. So the difference is less, so less fuel comes out. And as this is open more and more and more, it is subjected more and more to the manifold pressure, which manifold pressure at this point right here, we talk about manifold pressure in aircraft is a positive number. So we wouldn't really say vacuum, but for our sake, I think it's easier to think of this as vacuum here, less vacuum, less vacuum, less vacuum until we get to right here where it's nearly the same as ambient temperature. It's just about 1 inch less. So if standard day is 29.92, let's call it 30. Then right up here would be 29 inches. Outside to be 30 inches. We only have lost about a 1 inch vacuum, which is to say that this air pressure here is pretty darn close to ambient, close enough that this little hole right here is not going to have an effect. So once again, when this throttle plate is aimed right at that hole, air going between the throttle plate and that hole, that acts like a little venturi between the two, which is going to create a lot of suction, which is going to create a lot of suction in the float bowl, which is going to create a much leaner mixture. And as we open it, that mixture is going to get richer and richer and richer until we get to here, and there's no longer an effect on that little hole. So the back suction economizer system is no longer working. All right, let's take a look at the drawing and see if we can talk about it one more time. So right here is that little hole I showed you that's drilled. And you can see that right here where I'm showing you now, that's the throttle plate. So the throttle plate is here. At idle, everything up here is under a tremendous suction, right? A low pressure area. And we'll say that if outside is 29.92, 30 inches, we're talking about around 10 inches in here. So that's pretty low. No effect whatsoever on the economizer needle because it is down here that is all ambient 30 inches of pressure, more or less. But as we start to open it, that is the valve, and the valve starts to open, it is going to rotate down until it is pointing right at that hole, which means that there's a little escape right here between here, which I say is going to create a venturi here, creating probably the maximum amount of suction right here. That suction goes into here. That suction goes down into our vent down here, it's drawn a little bit different, which then creates a low pressure here. If a low pressure here, then we have less difference between float chamber pressure and venturi pressure, which causes the carburetor to go lean. As the throttle valve opens more and more and more, eventually it's open all of the way. Out here is 30 inches. All the way through here is 29 inches, and there's very little suction happening on that, which allows the carburetor to go rich. And again, that is called the back suction economizer system. So, all right, so back suction economizer system, we got that down. If you understood that, fantastic. I think we're both doing great then. All right, so the next system I want to talk about is the manual mixture control system. So let's change our system right here. We'll go back to this one right here, and we're going to talk about the manual mixture control system. This carburetor, as pretty much all Marvel Schebler carburetors, they have a mechanical mixture system. So as the aircraft goes up in altitude, the brains of the operation, the venturi, really has never been taught how to deal with altitude. It just senses the same altitude all the time. It really doesn't compensate for altitude. So we go up into altitude. We have the venturi working hard. It's saying we have, X number amount of suction. I have that much air flowing through. That's that much suction equals that much fuel going out. But the air around us is decreasing. The pressure is decreasing. We're up at altitude. And now the carburetor is running richer and richer and richer. And we already talked about why we don't want an overly rich mixture because of the waste of the fuel and the excessive lead and loss of power. So we want to lean out the mixture. We need to tell the carburetor, hey, we're up here at altitude. We need a little less fuel, please. And that is done through the manual mixture control system, which is controlled in the cockpit by the red knob right here. So we have rich and pull back for lean, or actually in the all the way back spot is called idle cutoff. So that's rich That's called idle cutoff. And what's happening is that is moving this valve right here, or this arm. This arm goes into the mixture metering sleeve right there. And so what happens when we are at full throttle, it means that this sleeve is wide open in here and doing absolutely no metering whatsoever. It is wide open, and the only thing that's metering any fuel is the main power jet. All right, but as we start pulling back on this shaft right here, the sleeve here, this rod right here will rotate and start blocking off that slot down there to the point where we get it so small that it's actually smaller in total than the power jet right there. Well, if this is the smaller of the two things, then this now starts doing the metering. And so that's exactly what happens. We keep pulling this back, making the slot down here smaller and smaller and smaller, which manually leans out the mixture until we get to a point where we pull this back so far, this valve actually closes off that slot completely, cutting off all fuel. And that is a wonderful thing to have, because this is how we would shut the aircraft engine off in this particular type of carburetor, which almost all engines have, unless it's got the Stromberg carburetor. That is exactly how you shut the engine off. You pull the mixture all the way out and the engine dies. So that is all there is to it as far as the mixture control system goes. Now, I will throw this out. It is not terribly uncommon to get an aircraft carburetor that has been overhauled, reinstalled on the engine, and the pilot or mechanic pulls back the mixture control into idle cutoff, and the engine keeps running and running and running, and it never cuts it off. Why does that happen? Because this rod right here didn't make it inside that sleeve. It's setting somewhere on the outside of it. So when you put it together, you must make sure that the sleeve and rod go together so the valve assembly fits in there. All right. So we have that going on right there. That is the manual mixture control system. Let's talk about the acceleration system in this carburetor. Now, at the beginning of the video, we did talk about the fact that this particular carburetor does not have an accelerating pump, but it does have a sort of a de facto accelerating system. So when we are in idle and we have fuel in the bowl, fuel is going to come up through here, and it is going to go through the idle system, as we already talked about. But what else is happening is, because the fuel level is right here, that means that, well, for certain, when the aircraft is off and not running, that this fuel is going to find its level in both the idle tube and the main discharge nozzle up to this line right here. So in the off position, fuel is going to fill up the fuel bowl. It's going to fill up to this level right here, the idle tube, and fill up this point right here, the discharge nozzle, as well as this area right in between where it's supposed to be air. So fuel is going to come up through the power jet and is going to come into here and go out all of the air holes and fill all of this up with fuel. And it is going to sit just like that until there is fuel drawn out. So we start the engine up, and now we're using the idle system. So fuel is going to come up this way, mixed with air, and then go up and then out the discharge nozzles for the idle system. But meanwhile, all of that fuel has filled up the air chambers here and this nozzle, so that when we open up the throttle and we start to draw fuel out, the initial charge of fuel that comes out is going to be rather rich, because we have yet to add the air into it. So there's a lot of fuel standing by, ready to go out. And that's kind of a good thing, because as we open the throttle up in an aircraft, we want to do it nice and easy and gentle, but there are situations where that's very difficult to do. You're coming in for a landing and something runs out across the runway, a deer or something, you get very excited, you hit that throttle to do a go around. You're not thinking, ooh, nice and easy. You're going to slam that throttle forward rather quickly before you hit the deer animal on the runway and heaven forbid, do a prop strike on your prop. That's very expensive, and it's also very hard on the animal. So you excitedly open the throttle, well, you're going to get a massive inrush of air through the carburetor. And if we didn't have extra fuel, then it would probably stumble or go a little bit lean right there. We need it to be not the carburetor and engine to not stumble, but do a nice acceleration. And so we have an extra charge of fuel waiting to go out, and that would be the accelerating well system. Now, the last thing I want to talk about here is how to set up this carburetor. These carburetors are actually very easy to set up, wonderful to work on. I love the Marvel Sheblers for that very reason. So we are going to just put this back together here a little bit so we can have a completed carburetor and talk about the setup for this carburetor. Now, the setup involves only two adjustments. We have the idle mixture, idle speed. Idle speed, idle mixture. Those are the only two screws that you can actually even turn on this carburetor to do anything. So makes it quite simple. Now, to set up this carburetor on an aircraft engine, what I like to do, first of all, is this is the idle screw right there, as I mentioned, and all it does is it provides a stop. When this arm comes back, you can see that it hits that screw. Where it hits the screw is how far open this butterfly will be. How open that far open it is how much air and fuel will get through and adjust the speed of the engine. If I were to take a screwdriver and just back this out a little bit, I'm going to close the butterfly valve. If I screw it in, I will open the butterfly valve. It's just that simple. It's just a stop for how much speed you want. So to set it up on the aircraft, what I like to do is back this out so that it's really not in effect. I don't want to mess with it. I want it out of my way. And then I will go in the aircraft and I will start up the engine and I will warm it up. So we want to do all of the adjustments on a warm engine. So I warm it up, and then what I do, and I'll use the throttle in the cockpit to set it at a nice idle speed. And so it's warmed up, and then I bring it to a nice idle speed inside of the aircraft and lock the throttle down, because most aircraft have a locking throttle, and I'll lock it exactly where I wanted it. All right. And then as it's idling, what I will do is I will pull back on the mixture all the way and watch it cut off. And the engine will die, hopefully. If the sleeve and the meter assembly are together, the engine will die. Now, when it dies, what we want to do is we want to watch the RPM, and we want to see about a 50 RPM rise and then die. So what happened, if that happened, is the engine, it indicates that the carburetor was running rich. In fact, so rich that we lost 50 RPM, but we didn't know it until we pulled this into idle cutoff. Then the fuel, as the fuel is exhausted out of the system past that mixture valve, the fuel then starts to lean out. And we can see the engine gain 50 RPM of power and then suddenly die. So that indicates we were on the rich side of power, or rich side of the power curve. It went up 50 RPMs, indicating that's its best power, and then suddenly died as it went super lean. So if we get that, we're good. But let's just say that we got 150 rise. Well, that means we were so rich that we're 150 RPM rich of best power. Well, that's way too much. We don't want it that rich. So we simply adjust this right here. And it says right on there, R and L, which is not left and right, it is rich and lean. And it tells me right there, if I want to lean it out, I will screw this in, which if we go to our drawing over here, remember this idle system right here? When we screw that in, there's a needle and seat, and we screw it in and we restrict this opening right here, decreasing the amount of fuel. So I will screw this in, decreasing the amount of fuel until when I pull it back to idle cutoff, I get a 50 RPM rise. Now, if I got no rise whatsoever, then that means that it's already on the lean side and I got a rich in it. So I will back this out and try it again. Start up the engine, pull this back, and if I get a 25 RPM rise and it dies, Well, if I want 50, I can just give it just a little bit more. Start up the aircraft, try it again, pull the mixture out. Once I get my rise right about 50 RPM, I'm happy. Then I will set the idle speed, because this will change the idle speed as you're working on it. So it's really difficult to set this screw first, then you set this and you go back to this and it's idling too fast. So trust me on that. Back this out, get your mixture set where you want it, then start up the engine again, set the throttle where you like it in the cockpit, lock it in, and bring this screw in until it just touches the throttle arm, and then we're set for a final adjustment. So again, in the cockpit, we start up the engine with it in full rich. We have it in idle. We check it. The engine is warm. We pull back the mixture, manual mixture control, and we should see about a 25 to 50 RPM rise in RPM, and then a sudden die. That indicates that we are on the rich side of best power. We're running rich. That's good for easy starting, and we are set to go. And it should idle somewhere around 550, 650 RPM, depending on what the engine seems to want to like on that. All right. Now, for some reason, you're working on this carburetor out in the field, and let's just say it's not a new carburetor, and you're being a diligent mechanic, and you're getting ready to do some work on the airplane. You've ran it, and you thought to yourself, hey, when I shut this down and I pull the mixture back, I should see a 25 to 50 RPM rise. And you do that, and you get no rise whatsoever. And you're thinking, well, that was funny. Somebody didn't set this up correctly. So what do? You're going to shut off the engine, you're going to get out, and you're going to open this up some more. So you open it up some. You get in the aircraft, go to full rich, start it up, you've got it in idle, and you pull the mixture back in, still no rise. What's going on here? Well, so you back it out a little bit more, and a little bit more, and a little bit more. And before you know it, you're pretty much got a loose needle right here. And you're thinking, well, that's not good. This thing's all loose, and the spring's not even working anymore, and it's hitting this right here, and this is not good. Well, what's going on with this carburetor? Well, one of the things about these particular carburetors, and probably the only negative that I'm aware of, is the bushings right here wear out rather rapidly. And you can do that. You can take it and you can move this back and forth. This one's very good shape. It's very tight. But these bushings right in here wear out. Well, when those bushings wear out, let's think about what happens. We've got it in idle. There's a tremendous suction right above here trying to get any bit of air it can. It's sucking fuel out of these little tiny holes. Well, it's also going to suck air from here and here. And if it's sucking a lot of air from there and a lot of air from there, that's air that's getting through with no fuel. You can back this out all the way, and it's still not going to get enough fuel to make it run at best power, or on the rich side of best power to say at all. So you'll never get a rise. So if you're backing this out, backing it out, nothing seems to happen, almost guaranteed you have an air leak here, or maybe even the gasket. But you have an air leak that needs to be repaired so that this will then function once again. So that's probably one of the things to really watch out for on this particular carburetor. All right, so before we finish off, I just want to cover a couple of things here that tend to catch people on these carburetors, and we want to be very careful of that. And that's a little bit of maintenance and airworthiness directives. So we talked about how to set up the carburetor properly, but I haven't yet talked about this right here. It is very important on any carburetor that you drain the fuel bowl out at least, and I'm going to say every 100 hours or every year. A couple of things. One, the more often you pull this plug out, the easier it is to take out. If you only do it once every 5 or 10 years, it can be very difficult to get that plug out, and you will not enjoy that job. But what happens inside of the float bowl is if you get any water into the system, the water is going to drop down to the lowest point into this little well right down in there. And you can get corrosion in there. Now, on some of the other carburetors, the outlet to the engine is much higher, and that leaves even more room for water down here, and that water will cause corrosion and ruin a carburetor bowl. So not only will it ruin the carburetor bowl, but if you get water into the engine quits, that will ruin everybody's day. So we do not want that to happen. So make sure you drain the bowl, I would say every year, every 100 hours is my rule of thumb on that. Now let's talk a little about airworthiness directives. This carburetor does have several airworthiness directives, and most of them are self-explanatory and easy to understand. But there are 3 that I want to hit on real quick. The first one is 72-06-05R2, and that deals with the throttle arm. And unfortunately, the AD is not well written in a way that it's easy to understand. And so I'm going to switch slides over here, and we'll hopefully the next one pops up. Let's see. There we go. So the AD talks about if you have a certain type of throttle arm, and one of the things it talks about is it milled flat or spot faced? And that's a term that a lot of people are not familiar with. And something that is milled flat versus spot faced is important to understand in the AD. A lot of people just simply look at those terms and go, well, I don't really know what that means, so let me guess. And let me tell you, if you want to be an aircraft mechanic, never guess, ever. Ask for help. Figure it out with somebody who knows. So something that is spot-faced means they have a casting, and this casting in its final finish process, they took a cutter on a mill, which a mill is very similar to like a drill press that allows a table to move around. So, and they will take a cutter that will, I'll use my flashlight here as the cutter. It comes down, it hits a spot and moves off. It was just spot faced. Like we could say that's spot faced. The cutter came down, cut it, and then was removed. So spot faced. But something that is milled flat, you would take the same cutter, and this entire surface up here has been milled flat. So the cutter then would go back and forth and mill this entire thing flat. So this is milled flat versus spot faced. So when you see this AD and they talk about this arm right here, was it milled flat or was it spot faced? Hopefully you will know the difference and be able to see which one should be removed from service and which one is acceptable. Now, the thing that is even more confusing is the fact that the AD never makes a reference to the new style throttle arms. So here you're reading this airworthiness directive, you're trying to figure out if this is milled flat or spot faced or what's going on. And the entire time it was non-applicable because the AD never addressed the serrated styles, what I call them. So if we look at the picture, the problem with this AD was this right here, this entire system clamped, and there was no positive engagement between we'll look at the carburetor here, between this piece right here and this piece. And so there was a potential for the two to slip, and you can imagine how bad that would be if you were in idle and you wanted to go full throttle and you push this lever forward, but this part right here that's pinned to the butterfly valve never opened. Well, then you wouldn't get full throttle, and that would be very bad for the pilot. So there was a procedure, looking at the drawing, whereby you had to make sure that you had the correct arm and safety wire it in such a way that the two pieces at least followed each other reasonably close should some slippage happen. Well, now they've changed out the throttle arms, and so there's this serrated type, which is clamped with this nut right there. There's no way these two are going to move because of the way they are locked into place. So this airworthiness directive would not apply, or more appropriately, it has been complied with by installing a different style of throttle arm. The next one that I would touch on just briefly has to do with the floats. Now, the floats have gone through some progressions on these carburetors. There have been these metal floats, there have been black composite floats, there have been white plastic floats. The problem with all of the ones I just mentioned is they were prone to failure. These particular floats, and especially the white composite floats, or I should say plastic because they were hollow, is that they get little pinholes in them, and those pinholes allow fuel to seep into it. And the surprising thing is the fuel will get in, but it won't get out. So it's very hard for these to be perfectly sealed, apparently. And not only that, they can be crushed. They're very delicate. So Marvel Schebler has gone to a new style of blue composite floats. So if you see this type of float in the field, the white float or the black float, they need to be replaced with the blue composite floats. So But there's an airworthiness directive on these particular metal floats. That would be 93-19-04, which talks about if you have a float with a part number CF30766, that you need to pay attention and has certain dates you have to remove it. And the point I want to make here is, I don't know if you can see that in the camera, but it's definitely a part number 30-766. But what did the Airworthiness Directive say? It said part number CF30766. This does not have a CF on the beginning. And the point here is that there are several different manufacturers of parts for these carburetors. And CF stood for, I think, Consolidated Fuel Systems. It was their product. So the point I want to make is, if you see a part number 30766, but it didn't have the CF was part of the part number. Don't just skip over that. The letters and numbers all go together in the Airworthiness Directive. And that's not really something to do with floats per se. That's on anything in aviation. Read the whole part number. Don't just leave off part of it. I have students all the time. I'll say, well, does this apply? And they'll say, well, yes, it does. Well, it doesn't. It doesn't have a CF. So this is made by somebody completely different. So it didn't apply. And the last one I want to talk about is the Venturi. And there is an AD 780106 on the two-piece Venturi. This one's a bit of a head scratcher for me because this is a single-piece Venturi, and I can tell that just by the way it's manufactured. The old two-piece Venturis, this primary Venturi actually could come out and leave the secondary in there. This is a one-piece. It's all manufactured together. The old two-piece was split right in here, and there were these three little clips that held this primary in. Well, that primary would get loose and get ingested into the engine, which was a very, very bad thing. So Marvel Schebler said, well, you need to go to a new one-piece Venturi. And that made a lot of sense. But here's the thing that's confusing is that this Venturi looks exactly like the old two-piece. I mean, they look so identical that it really takes somebody who's overhauled these things and familiar with them to be able to identify, oh no, that's a one-piece. I know where to look. Anybody who opens it up who's not experienced that will say, yeah, I don't know. I can try and pull this out. And if it doesn't come out, I guess it's a one-piece. But what is so interesting is they look so identical, yet Marvel Schebler had a lot of problems when people went to the one-piece Venturi of the engines no longer running very smooth. They had a horrible time getting the engines to run smooth. And so in the Airworthiness Directive, it does talk about different style of nozzles. So you may see a different style of nozzle that was used in that carburetor to get that one-piece Venturi to actually work appropriately in that engine. So it was a very strange thing. But I guess the point there is, number one, be aware that you need to have the one-piece Venturi. If you have a two-piece, you have to inspect it fairly often. And number two, you may have a different style of nozzle in there. And if you were working on that carburetor and for some reason wanted to change out the style of nozzle, I would be hesitant to do that if the owner said, no, that the combination was working great. You may end up going to a nozzle that didn't run quite so well. So there we have it. That is the Marvel Schebler MA-3A carburetor. And I hope you enjoyed that one. Please click that like button. If you have any questions, leave them in the comments or contact me at the school, and I'll be happy to help you. Take care. Bye.